So let's begin. Today we cover section 8.1, arc length. This is the last chapter before the midterm, and this won't be on the midterm. It will be on the final, though. So let's think about a curve. And suppose we want to know the length of this curve. So we know exactly how to measure length of something that is straight. We take a ruler and measure it. If we have a curve, the task becomes more difficult. So one possible method would be to take a string, align it along the curve, then straighten it and measure it with a ruler. Okay, so that's one method. There is another method that we can implement here, which utilizes calculus. Okay, and the idea is as follows. Let me draw it here. So if we have something like this, we can roughly pretend that this piece consists of a bunch of straight segments, okay, like this, and measure the length of each segment. So that's going to be an approximation to the length of this curve, intuitively speaking. To make the approximation better, of course, we can make more segments. That is to refine our approximation. So we can put more intermediate points. In this process, we can get better and better approximations of the length of this curve. So if we put it in a coordinate system, let's suppose this is x and y is f of x. Okay, we can split this into a bunch of points. So we make a partition of the x-axis. So this is x1, x2, and so on. And this is b, xn, x0. Okay, so as usual, we create a partition. Each partition identifies a point on the curve, and we connect these points like this. We can name these points P0, P1, P2, and so on, Pn, right? And now the length of each straight segment can be denoted like this. So P0, P1 is length of segment P0, P1, right? So if we add them up, we get an approximation to the length of this curve. So we can create a sum where I goes from 1 to n. And here we put pi minus 1 pi. Okay. So each of these is straight segments. We sum them up, and to make the approximation perfect, we take the limit as n goes to infinity. And finally, we say that this is equal to the arc length, the length of the curve. Length of the curve. Okay. So this is definition. Question?
Yes. So is that p sub naught times p sub 1?
This is not times. So this explains the notation. If I have a segment between points pi minus 1 and pi, the length is denoted by this pi minus 1 pi.
Okay, so
there is no multiplication here. Okay, this is just a notation. We'll put the 2 points. So the interval is denoted by pi minus 1 pi, and when we put the absolute value sign, that signifies the length. Okay, it's just a notation. So what we are doing here, we're measuring this, plus this, and so on, to approximate the curve, okay? The length of the curve. Questions? Fine. So we can actually design a better formula. With this, we cannot do very much except for actually doing it, right? Splitting it into a bunch of points and measuring, putting a ruler to the curve. But we can do better. So let's assume that f of x has a continuous derivative. This means that this function is smooth, mathematically speaking. It doesn't have any cusps or angles like this. So in this case, we can derive a much better formula for the length. Okay, so let's consider the length of segment pi minus 1 pi. What is it equal to? So if this is pi minus 1, this is pi in my coordinate system, this point corresponds to xi minus 1, yi minus 1. This point corresponds to xi, yi, right? So we are measuring this length. What's it equal to? We're making a triangle. This side is xi minus 1, and this side here is yi minus yi minus 1, right? So to calculate this length, we take a square root of the following familiar expression. Okay? So that's pretty clear. We can also denote it as delta x squared plus delta yi squared. This is just a notation to denote these differences. Now we're going to use the mean value theorem. By the mean value theorem, we can express delta y I as f prime of xi star times delta x. Okay, what does it mean? It means that there is a point xi star such that the function f has a derivative evaluated at this point that satisfies this equality. This is the material from the first part of your calculus 2a, and perhaps the name sounds familiar. Okay, so the point here is that we can replace delta y with something times delta x. So let's do it here. So we can say that pi minus 1 pi is the square root of delta x squared plus delta yi squared. And now instead of delta yi, I'm going to put the expression obtained from the theorem, f of x I star delta x squared. And now, of course, I can take the delta x squared out like this, and I have 1 plus f xi squared. And finally, I can take the square root of delta x, it's a positive quantity, and under the square root, I'm left with a simple expression like this. Okay? So now I can use this formula to express the length of each segment. You see, it takes the information about the actual function f, that whose curve we're measuring. So let me continue writing here. This is my definition of the length of the curve. Okay. So instead of this segment length, I'm going to substitute that formula that I derived. So we have a limit n goes to infinity of the sum of square root of 1 plus f x I star squared delta x. And now the last crucial step is to recognize this as a Riemann sum and to rewrite it in terms of an integral. You can see that we have something evaluated at a sampling point inside each interval times delta x summed up and a limit. So very easily, this can be recognized as an integral between points A and B of this quantity, 1 plus f prime. I'm sorry, this is f prime. F prime. Can you please go back? I forgot to put the prime. Squared dx. And this is a formula we can work with. This is something that we can evaluate by doing integrals. So this gives us yet another application of integration. We already saw how to calculate the area under a curve, area between curves. We calculated volumes of various solids. And now we can calculate an arc length, a length of a curve. Another notation for this, we can say that f prime, and of course there's no star here, because this means sampling point. When we go to integration, there's no star. So f prime of x can be written as dy dx. So this integral is 1 plus dy dx squared dx. Okay, so this is either this formula or this we can easily use to evaluate the length of a curve. The first example is the following. So let's consider the curve y equals x squared over 2 minus log x over 4. Calculate the length of this curve from x equals 1 to x equals 2. Okay? So we can draw this function or not. In this case, you can see that it's a regular function. It's continuous. It has a continuous derivative. Everything is fine. We are going to apply this formula to calculate the length. So a is 1, b is 2. These are the given values of the variable x. Okay, so what do we need? We will need the square root of 1 plus dy dx squared, right? So this is the object that we always have to calculate when we measure the arc length. So we do it step by step. So first, let's calculate dy dx. So this is 2x over 2 minus 1 over 4x, right? Or we can simplify it to this. That's the first step. Next, we do dy dx squared. So it's x squared minus 1 over 2x plus 1 over 16 x squared. 1 over 2, rather, not 2x, like this. Next is 1 plus dy dx squared. We have to add 1 to this. So x squared plus 1 minus 1/2 plus 1 over 16 x squared. And now we simplify. X plus 1/2 plus 1 over 16 x squared. And actually, we can simplify even better. you know that eventually we're going to take a square root of this expression. So it would be nice to recognize this as a full square. Look at this expression. It only differs from this full square by the sign in front of 1/2. So we can see that this is really x plus 1/4x squared. Okay? And this makes it really easy for us to take the square root as the last step. So the square root of 1 plus dy dx squared is given by x plus 1/4x. And this is the object that we are going to integrate. So let's go here. The length is the integral between 1 and 2, 1 plus dy dx squared dx. And I replace this expression with what I obtained, x plus 1/4x dx. Okay? So this is the usual procedure. We have to remember this, the general formula, right? And we do it step by step. First, we evaluate the derivative, dy dx. Then we square it, add 1, and try to extract the square root of that. And this is what goes in here. It's not always possible to, find the full square there. But we can always try. And now it's really easy. We take the antiderivative. Between 1 and 2. So what do we have? 4/2 plus 1/4 log 2 minus 1/2 minus 1/4 log 1. Okay. So log 1 is 0. And 2 minus 1/2 is 3/2. And we have log 2/4. So this is the numerical value of the length of this curve. Questions? Okay, I'll give you another example. Find the length of the curve x squared equals 4 y plus 4 cubed between where y ranges between 0 and 2 and x is positive. Okay, so this problem is a little bit different. We have a range in y, and we have another condition that x is positive. You can see that this curve has a couple of different branches. It's not a function. If we express x as a function of y, we get two solutions, plus and minus square root of this expression, right? So there's going to be stuff for positive values and for negative values of x. And in this problem, it's actually better to integrate in y rather than in x. And that's what we're going to do. So we will we'll solve for x. Okay, so we say x is square root of plus square root of 4 y plus 4 cubed. Why is it plus square root? Because of this condition, right? We are given that we want the length of the branch that corresponds to positive values of x. Okay, so we take the positive square root, which gives me 2 y plus 4 3/2, and we perform integration in y from 0 to 2. Okay? So what is my formula going to be like? It's going to be an integration from 0 to 2. And look what I have here. Instead of dy dx, I'm going to treat x as a function of y. So I have dx dy squared dy. See? So this is a twin sister of the formula that I derived here. How come I didn't derive it? Very easily, because when I look at the curve, I can put like a curve like this, right? I can put my coordinates like this. So this is x and this is y. Or I can put my coordinates like this and interchange x and y. The curve doesn't care. Its length certainly remains the same, whatever we do with our coordinates. Okay? So it doesn't matter which axis you call x and which axis you call y. So you can either use this formula, where we have dy dx and we integrate in x, or we could have dx dy and integrate in y. It's the same formula. Okay? And here it's more convenient to perform it in y. So the next steps are standard. We start with dx dy. So all the components of this formula. So we have to differentiate this equation. So we have 3y plus 4 1/2. Okay. Next, dx dy squared gives me 9y plus 4, and the square root goes away. Next, I have 1 plus dx dy squared. I have to add 1. And finally, I need to calculate the square root of 1 plus dx dy squared. So what's that? That's square root of 1 plus 9 y plus 4, and that's it. Okay? So this is the expression I will use. So the length goes from 0 to 2, 1 plus dx dy squared dy. So rewrite it with this information. What kind of function is it? Is it easy to integrate? Yeah, this is just the square root of y plus something. So a simple substitution will work. Before I do that, I want to open the brackets here. So this becomes 9 times 4 plus 1 is 37 plus 9y dy. Now you can see that it's easy. What's the substitution? We say u is that whole thing, 37 plus 9y. du is 9 dy. Okay? And when y is 0, u is 37, 1y is 2, u is 55. I have to change the limits of integration, right? So these are all the steps with substitution. Any questions? So go from 37 to 55, square root of u du, and I have to divide by 9. Okay, so I have 2 over 27 u 3/2 from 37 to 55, and this gives me 2 over 27 55 3/2 minus 55, or minus 37 3/2. Okay, so this is the numerical answer for this curve. Questions? Question?
Why did it turn into 3?
Say again?
It says dx or dy. Is it 3 in front of it? Yeah.
Here?
Yeah.
Yes. I have to differentiate this expression. So it's 2 times 3/2.
Oh, okay.
So 2 cancels.
Okay.
Okay, so the next little application of this is quite natural. We're going to do the following. Let's suppose we have a curve, okay, and we have some starting point, P0, okay, and we want to know how the length of the curve changes as we travel along, okay. So we're going to, like, if this is our x-coordinate, we're going to make a variable, a variable that slides along the curve. And we want to see what's the length of the curve from here to here. Then I move it. What's the length of the curve from the beginning up to here, and so on. So that defines the arc length function. Arc length function. So we call it S of x, and it's an integral from A, not to B, not to some fixed location of the end, but from A to variable x. And here I have the same, except I'm going to call my variable of integration t. Okay, so maybe okay, call it x. So the upper limit of this function is my variable. I want to know what is the arc length from the given point up to any limit, okay, along the curve. We can use the fundamental theorem of calculus to calculate the derivative of this function with respect to x. And you can see that straight from that theorem, it gives me this squared, squared, okay? Or we can say that it's 1 plus dy dx get x squared. I can write it, multiply by dx, and I get dx equals this, dy dx squared dx. Now I can square the whole thing. Let's square it. I have ds squared equals 1 plus dy dx squared dx squared, okay? And I can multiply by dx through, so I get dx squared plus dy squared. So to rewrite this all together, I get ds squared equals dx squared plus dy squared. This looks familiar, right? Especially if I think of it this way. So dx is an increment in the variable x, like this. dy is the increment in y. And ds is the arc length of corresponding to this increment. So let's suppose that my current variable x is here. I increase it by a small amount. Y also changes by a small amount. What is the increment in the arc length? It corresponds to this curvilinear segment, its length, right? And this is not really a triangle. It has a straight side, and a curvy side. But when the increment is really, really, really small, then the curvilinear side satisfies this equation, the Pythagorean theorem, right? This dx squared plus dy squared equals the square of this length. So this tells you that in the limit, when these two are really, really small, we can use this simple triangular identity to calculate the arc length of that very small segment. So it's just something that follows directly from this formula. We don't have to use it. We can just use this formula to calculate the arc length function. I'm going to give you an example where eventually we will be able to compare the result that we obtain with a formula that we know, because we will be dealing with a circle. So here's the setup. Let's suppose we have a circle. Find the arc length function for a circle of radius r starting from the point 0 r. So this is radius r. This point here is 0 r. And x positive. Okay? So we're going to go from here. X is going to change from 0 and grow. And the values of the arc length function will correspond to the length from here along the curve. So let's do that. First, I want to express y in terms of x. So the equation for this circle, as you know, is this. For the first quadrant, we can say that y is the square root, positive square root of r squared minus x squared. Okay, so the arc length function, what's notation, sorry, s of x is going to be equal to the integral from 0 to, let's call it t. Okay, let's call it x. Square root of 1 plus d f prime of t squared dt. Okay, so here in this notation, my silent variable of integration is the x coordinate here. And this x on top is where I stop integrating. Okay, so we can write down f of t is square root of r squared minus t squared from this. So y, the y coordinate is my function f of t. And it's given by this. Instead of x, I put t everywhere. Now I have to go through all the steps. Let's calculate f prime of t. I have to differentiate this expression with respect to t. So 1 over 2 square root of r squared minus t squared. And I have to use chain rule. So I multiplied by minus 2t. So to simplify, I have a negative t over r squared minus t squared square root. So this is f prime. The next step is f prime of t squared. So that's t squared r squared minus t squared. Next step is 1 plus this. So I have to add 1 to this expression. R squared minus t squared plus t squared divided by this. So I get r squared. Everything simplifies quite nicely. at each step almost. Finally, what is the square root of this? I have to take a square root of this, so I have r divided by square root of r squared minus t squared. So this is what I'm going to use in my integration. So an integral from 0 to x, r divided by r squared minus t squared dt. Okay. So I'm going to take r squared from outside, put it outside the square root. So I have 1 minus t over r squared, like this. Okay? And here I have r dt. Fine. So one more step before we do a change of variables. I'm going to cancel this capital R. So this is an easy integral to take, right? It's just one short step. I need to use an intermediate variable, u. Substitution. So let's do it here. So we have an integral from 0 to x dt. So my new variable u obviously is going to be t over r. du is dt over r. So when t is 0, u is 0, and when t is x, u is x over r. So these are all the changes. Don't ever forget to change the limits of integration. That's probably the most common mistake when people do when they have a definite integral. So we'll go from 0 to x over r. And we have an r here, du 1 minus u squared. So what's the antiderivative? Arc sine, exactly. So this is something that we should remember. Arc sine of u between 0 and x over r. Well, almost done. So we can say that, well, this is equal to r sine minus 1 of x over r minus sine minus 1 of 0. What is the arc sine of 0? Is 0, right? Therefore, we can say that the arc length function s of x is given by r sine minus 1 of x over r. You give me x, okay, for instance here, and I tell you the length of the curve from my initial point to the point with coordinate x. Okay, so this is what this function measures. It measures the arc length between this given point and any x that you want to give me. So how do we check this formula? It's a circle, right? So we know a few things about the circle. For example, we know the arc length between here and here, because this is a quarter circle. So we expect that s from here to here, so s of r, when x is equal to r, equals the circumference, the length of the full circumference divided by 4. What's the length of the circumference? 2 pi r divided by 4. So that's pi r over 2. Okay? So let's check it. S of r. Here we have to substitute r instead of x. So we have r sine minus 1 of r over r. So we have sine minus 1 of 1. What's that equal to? What's the arc sine of 1? What's the angle whose sine is equal to what? Pi over 2. And, of course, this is this checks with what we expected, right? Any questions? Question?
Why is it t over r?
Where?
At the end of the integrating.
Here? 2 over r.
T.
T over r. Oh, so here I have r squared minus t squared. Or I can say r squared 1 minus t squared over r squared. Like this. I take r squared out. So if I multiply this through, I get r squared minus t squared, right? And then the rest follows, right? Question?
Yeah, I missed a little, I think I missed a step. So at the very beginning of this side over here, you have dt divided by the square root of 1 minus t over r squared. And we said that u is t over r and du is dt divided by r. So why is it r times that quantity?
Because dt is r times du. So instead of dt, I have r du. More questions? Okay, very good. I'll give you one more example. Let's do this one. So these examples I always like because we can check what's going on. Oh, one more comment about this. I think the formula that we derived actually only works, this formula, okay? This only works for x, to calculate the arc length between this point and anywhere up to here, okay? If I want to go further, this formula will not work. Because when I derived it, I first wrote down the equation of the circle, and then I resolved for y, and I said y is positive. So this is a positive square root. So if I want to go over, this formula is not applicable. So to calculate the arc length from here to here, one method would be to say it's equal to this length, the quarter of a circle, plus the new arc length function, which I would have to set up starting from here to another variable. Okay, okay, but these are details. The last example. Find the arc length function for the curve y equals x squared minus, one second. Squared. One over 8x. Taking p naught 1 1. Okay. So we have f of x. It's very similar to the example that we already had, but instead of a fixed length of the curve, we're going to design a function. Okay. So we can write down this expression. 1 plus, we have to differentiate this. 2x minus 1 over 8x squared. That's given by 64x squared. And again, just like before, we can recognize this as a full square. like this. So actually it works out to be (2x plus 1 over 8x squared). So the square root is simply 2x plus 1 over 8x. So what is s of x? We start our integration at 1. We go up to x. And here we replace x with t, the silent variable of integration, f prime t squared. Okay. So I go from 1 to x, and I use this expression, 2t plus 1 over 8t dt. Fine. So we take the antiderivative. So it's simply t squared plus 1 over 8 log t between 1 and x. This is equal to x squared plus log x over 8 minus 1. Okay. So s of x is x squared plus log x over 8 minus 1. So what is the arc length between points P naught 1, 1 and P1 3 f of 3? Question?
Yeah, I thought the original function was, or the last part of it was 1 over 8x, so how did that become f of x is equal to x squared minus rational log of x, the very top?
Here?
So that says 1 over 8x, so why does f of x become ln x over 8?
Oh. I'm sorry. This was 1 over 8 log x. I already took the derivative here. Log x over 8. Thank you. So this. Thank you very much. So we want to calculate the arc length between this given point, P naught, and another point, which is 3 and f of 3. What's f of 3? So this is 3. F of 3 is 9 minus log 3 over 8. This. Okay. So this is very easy. All we do is we say that s, the answer is given by the arc length function evaluated at point x equals 3. So we just say s of 3 is equal to 9 plus log 3 over 8 minus 1. So it's just 8 plus log 3 over 8. And for any other point, we do the same, and that gives you the length of the curve. Any questions? Question? Minus 1 is this, and this gives you 0. More questions? Okay, thank you very much.